Then how about let's get started? Yeah.
Sure, definitely, yeah.
Okay.
All right. All right. Good afternoon or good morning, depending on where you are. Thanks so much for joining us for our YSI virtual webinar. And here, we just before we get started, jump into the exciting talk itself. I just wanted to quickly share with everyone here that our mission at the YSI Center at Iowa State University, and also for the whole webinar series, like what are the goals and the long-term vision we have. So for YSI Center, like the two most fundamental missions. The first one is to connect the unconnected while advancing the frontiers of all the mission critical wireless applications. And the second one is democratizing research, education, innovation. These are more important. These are very important aspects. And then some examples, including the ARA wireless experimental testbed, being developed and deployed at the Iowa State, and also our OTIC that is more in the ORAN context. And then next for the whole webinar series, this is, if I remember correctly, this is our fourth virtual webinar now. And the whole, like the long-term vision we hold is that we would like to share insight from all the thought leaders in the wireless community, and also like rural wireless agriculture, all the related fields. And then by doing so, we'll be able to build a community around these key wireless innovations. And some example areas could be HRLC, spectrum innovation, AI, 6G, ORAN, and all the open source related projects. And so, and then the final piece of information is that if you feel like you have some exciting work to share with our community, feel free to contact us at YSI or directly contact me. And here's my email, and then some QR code for you to scan if you like. And with that, I would like to give the floor back to Professor Hong Wei, our director at YSI Center, and to give an introduction of our speaker, Professor Jin Yang today. And I would like to, so then with that, I will just stop sharing here and feel free
All right.
to.
Thanks, Jay. If I may just add one point to what Jay shared, it's our first exercise for doing that summary over there. Essentially, one of the effort we're leading here is the ERA Community Wireless Living Lab, right? So with that in mind, we feel, and there's actually a way to potentially open up new opportunities of collaboration and learning through such community platforms and also associated data, other collaboration opportunities. In fact, I didn't know actually Jim until I get to know another friend through the ERA discussion, and had a great pleasure actually working with Jim on one of the recent proposal effort. Yeah, so it's a great pleasure to have Jim with us actually. So I'll do a just quick intro, and then we'll give the floor to Jin so you get to hear all these good ideas that's there. Yeah, so Jin is currently a associate professor at University of Virginia, and her research has been focused on what I guess most people are excited these days, transformers, large language model, reinforcement learning, also the privacy preservation aspect of those machine learning techniques, and then of course the applications in wireless communications and networking. She has been a leader of the community in many ways, have been serving the leadership team for conferences, all sorts of conferences you can find in the web, on the web. Actually, that's in the announcement. Also as the area editor and editors for several leading journals in our community, like IEEE transactions on green communications, transactions on wireless communications, and so on. She has also received many awards, including the NSF Career Award, and also for the ladies in this talk, there are actually I think communities in the networking community, including networking women, and women in communications engineering. She has been recognized in that community, for example, with awards such as Early Achievement Award and the Stars in Computer Network and Communications Award there. So I guess it's nice to be lady in the networking community. So we can probably focus on also try maybe either offline or live here. You can get insight advice from Jean. So with that, let me actually give the floor back to Jean. Maybe Jean, you can take it from here.
Sure. Okay. So can you see my slides right now?
Yeah, very well.
Okay, sure. Let me. Okay. All right. Thank you, Hongwei, for the nice introduction and also for the invitation as well. Also, I'm very happy to speak here today. So I would like to share some of our recent works on augmented in-context learning and its application for wireless symbol detection. This is a joint work with my student Ren Pu and my collaborator, Professor Cong Shen, at University of Virginia, as well as his students, Li and Wei. So let's start with the basics. So what is in-context learning? In-context learning, or ICL, is the capability of a large language model to learn a new input-output mapping from examples provided directly in a prompt. So during this process, it doesn't have to change or update its parameters, and it can, conditional on the demonstrations or examples to directly output the corresponding, prediction. So here I give an example. So imagine, there is a prompt from a user which contains several demonstrations that translate some, English phrase to the corresponding Chinese phrases. And then, it also gives, a so-called query, which is an English word. And then, conditional on the given demonstrations, the model will automatically output the corresponding translation for the English word goodbye. So in this process, large language models doesn't have to do any gradient update or fine tuning. It's automatically adapts to the new translation task here in this inference stage. So this is a very amazing capability. It enables fast adaptation to new different tasks with a single model, and it has very wide applications in different tasks such as classification, translation, summarization, and so on. Okay, so one fundamental question here is, why transformers can actually perform so-called in-context learning? There are recently some theoretical works trying to explain the underlying mechanism of ICL. So there are some, complementary perspectives. So for example, some works interpret this from a function approximation perspective. It basically views transformers as some, function mapping that directly maps the corresponding, prompt into some output, such as performing, linear regression type of mapping. Another perspective is to interpret this process as some sort of posterior inference. So in other words, it can emulate some Bayesian inference process over some latent variables. So conditional on the input, given in the prompt, it will infer the corresponding posterior distribution on those variables and then output, the corresponding, predictions based on sampling of of those latent variables. So another interpretation is to view this as, this process as some sort of optimization. So it basically proposed the idea that transformer actually emulate some optimization process during this ICL process. So for example, it may actually implicitly do some gradient descent during this forward pass, so that, after a few layers or iterations, then you can eventually solve some sort of optimization problem. So motivated by those complementary theoretical explanations, so in this work, we try to study a new or variant of the SAL problems, and we are trying to give some theoretical explanation, for this new setting. So this is so-called SL with augmented data. So the motivation of this problem is like this. So we note that conventional SL or standard SL relies on labeled examples. So usually you have inputs and you have the corresponding output, which is the input-output pair, such as the English-Chinese translation pair. So you have such pairs, or demonstrations in a prompt, and then the performance of the prediction is based on the quality or the data provided in those labeled examples. So, but for many applications, obtaining such labeled examples is actually very expensive, especially if expert annotation is required. So then how to handle such data scarcity, right? So there are some approaches handling this challenge from different perspectives. So one approach is to basically synthesize some labeled examples. So although, we don't have so many human labeled examples, but we can synthesize some examples based on learned statistical relationship from those labeled examples. And then based on the synthesized examples, basically, then we can, repeat this standard SL process. And another similar idea is to, again, use large language model to generate some so-called pseudo labels of unlabeled data. So you have some, X, but you don't know the corresponding Y, and then you use the large language model to generate the corresponding Y, and then, with the pseudo labels, you essentially get some labeled examples, so you can do standard SL. But we know that in this process, because it's you rely on the corresponding large language model to synthesize either the examples or the labels, and this is inherently limited by the underlying capability of the large language models. So in this process, you may get some wrong information, incorrect information, or even biased information. So then that motivates the following approach. So we want to directly use some unlabeled data together with the labeled examples in a prompt without synthesizing or generating the corresponding pseudo labels. So the question we try to answer is, can we provably improve the SEL performance of transformers by directly using such unlabeled data together with the limited labeled examples? So to answer this question, let's first visit, the underlying transformer architecture, because this is the building block of those large language models, and understanding how transformer works can help us understand how the ICL capability emerges. So transformer usually is a stack of attention layers followed by feed-forward layers. So usually there is a block like this. So in this block, we have a so-called multi-head attention layer and followed by a feed-forward layer. And then, those blocks are, stacked together, and then depending on how such transformer blocks are connected, we have different variants, such as so-called encoder-only transformers, which is the building block of BERT-style large language models, or decoder-only transformers, which is the building block of GPT and these variants. And of course, there are also so-called encoder-decoder transformers, which is usually used on some, language translation tasks. So if we take a closer look about the attention layer, because this is a core, the self-attention mechanism is the core of transformers. So if you look into the attention layer, we can see that for each input token, which is denoted by the X here. So here we have, two tokens, basically. Each row is a token. So for each input token, the attention layer will map it into 3 different vectors. One is the so-called Q vector or query vector. The other is the key vector, or it's just the key vector, and the v vector or value vector. So through those transformations, so basically the input token is going to be multiplied with some matrices and then mapped into those three different vectors. So those three different vectors actually represent different physical meanings. So for the Q vector, basically it represents, what this token is looking for. And then the key vector indicates what does this token contain, which information does this token contain. And the value indicates which information this token will contribute if it's attended to. Okay, so with those three vectors, then the transformer will do some operations. So it will calculate the similarity between the Q, which the query vector, and the key vectors from all the other tokens. So now you're going to the similarity is captured through the inner product and then passing through the softmax function. So then, intuitively, this similarity will indicate how much, the current query token is going to attend to the other tokens based on the similarity between those Q and the key vectors. And then with the, with the softmax, weight, the corresponding value vectors of all those tokens will be, aggregated together. So this will give, the corresponding so-called attention. So intuitively, this self-attention mechanism enables the tokens, to extract information from other relevant tokens, and use those information to get the so-called attention. So so although this formula looks a little bit complicated, but essentially, what we can understand is, so the parameters of those matrices together with the softmax function or activation function will determine which kind of information you will get out of the transformer or out of the attention layer. So formally, given the input embeddings H, so here we have a matrix H, which is basically a collection of token embeddings. So each column is going to be, a token or token embedding. So now you have a input sequence of tokens, and then with, this as the input to the corresponding attention layer, the transformer will perform the softmax operation based on the key and the Q vectors, and then multiply with the corresponding V vector, and then sum over different heads. So basically each head is capturing different dependencies among those tokens. And then this pass part is basically the residual part. So then, this is what mathematically an attention layer does, based on the input and its own parameters. So here we have a sigma here. Basically, this sigma is a nonlinear activation function, and in our previous slide is simply the softmax function. But it can also be set as, in other different forms. So after this attention layer, the corresponding output of that layer is going to be fed into this MLP layer. So MLP layer, is another, operation, on the input tokens. So basically, we can select the corresponding matrices W and the vector B together with the activation function to map one input embedding or input token into another token. So so together, the attention layer and MLP layer, stacked together and form a transformer layer. So usually for large language models, there are many transformer layers stacked together. So the, essentially it makes the model larger, more complicated, and also more expressive. Okay, so here our goal is to understand how a transformer can actually perform augmented ICL and trying to understand the corresponding performance guarantees. So to achieve that, we consider a controlled case. So we consider a multi-class linear classification problem. So this is a simplified problem, but also it has wide applications, as we're going to see later. So here, this classification problem consists of C classes. So we assume there are C different classes, and each class, has a center represented by this vector mu. So all those mu i's are indicating the class centers, and all the samples from the same class is essentially a noisy version of this sample. So we assume the noise is Gaussian, and the sample is related to the class center in this way. And then we assume all the samples are uniformly drawn from those C classes, and and also all the samples are for samples from the same class, they are drawn in an IID fashion. So now we consider a prompt with unlabeled samples, which means, for all those xi's, x1 up to xn, we know exactly which class it comes from. So we have the corresponding indicator y or label y to indicate, the associated class. And besides those labeled samples, we also have M unlabeled samples. So we denoted them as xn plus 1, so on and so forth, up to xn plus m. So together we have, those labeled and unlabeled samples in the prompt. And then our objective is to use this prompt to predict the corresponding label of the unlabeled samples. So in other words, we try to predict yn plus 1, yn plus 2, up to yn plus m during this in-context learning process. So as we can see, if m is equal to 1, which means we only have one unlabeled sample, then this essentially reduced to conventional ICL. But here, we allow m to be more general, so this is a more general setting. And we try to understand if we, include more unlabeled samples here, what's the corresponding impact on the ICL performance. Okay, so intuitively, we would expect that those unlabeled samples can actually help us to improve the ICL performance. So to understand why this is the case, so here we consider a very simple example. So here we consider two classifications. So it's binary classification. So the center of those two clusters are indicated by those two dots here. So you can see the center of this this red and the orange and the blue circles are here and here. So those are the class centers. And then you can randomly sample some data from the corresponding clusters with the Gaussian noise. So now if we consider a case where we only use labeled samples, so which are denoted by those triangles here. So we have a blue triangle here, and we have an orange triangle here. So let's say your transformer is given those two labeled examples, means, okay, we know where they are, and we know the corresponding class it belongs to. So we know this sample belongs to the blue class, and this sample belongs to the orange class. So now with the coordinates of those two examples and the corresponding labels, so based on our knowledge of binary classification, under the uniform prior distribution, we know that the optimal decision boundary is actually this red line. So in other words, we this is a line passing through the middle point connecting those two examples. So theoretically, we can show that if we do it in this way, then this is the best we can do. And then, obviously, this decision boundary will give us a large prediction error, because as we can see, for any samples that, the orange samples that is lying on the left side of this red curve, they're going to be labeled incorrectly, which means, we're going to have a large classification error for case like this. So this is what would happen if we only do the classification based on the labeled samples. But now let's imagine, okay, on top of those two labeled samples, we are actually given a bunch of unlabeled data drawn randomly from both of those two clusters. So now let's say you have some blue samples, collected from this cluster, and some orange samples collected from the other cluster. So for those samples, we just know their coordinates, but we don't know their, the corresponding labels. We don't know exactly which class those samples belong to. But then, we can do some clustering, and, a simple clustering procedure can indicate that, okay, we're going to form a cluster roughly, on the left-hand side, and another cluster on the right-hand side. And then, this labeled blue triangle most likely is going to fall into the blue cluster as well, and similarly for the green, for the orange one. So now if we utilize, the cluster structure as well as the label that is, contained in the paired examples, so we might be able to have a better decision boundary, which is indicated by this purple line. So you can see that, okay, although those unlabeled data does not directly provide their labels, does not give us their labeled information, but by utilizing the clustering structure, the geometric structure embedded in the data, we can actually improve the corresponding classification performance. We can, have a more accurate decision boundary, which leads to lower classification error. So that is one intuition why unlabeled samples can actually help. So then the question is, okay, intuitively adding more unlabeled samples can improve the classification performance, but can a transformer actually learn and leverage such a geometric structure from the unlabeled data during this in-context learning process? So to answer this question, we introduce an approach called chain of thought prompting, or COT prompting. So COT is actually, a prompting technique that has achieved very impressive performance in various tasks of large language models. So one COT prompting example is given here. So for example, if we want to ask the language model to solve some math reasoning problem for us, such as, okay, if 5x equals 10, what's x squared? And we indicate that, you should think step by step. So with this prompt, then the corresponding large language model is going to generate some intermediate steps. So it will first, based on what's given here, calculate the value for x, which is 2. And then based on the result from the first step, it can move on to the next step and calculate x squared, which is 4. So by generating such intermediate steps before directly outputting the prediction, so this technique can actually improve the reasoning performance of LLMs, for different tasks. So if we formulate this process, the COT process, from a mathematical perspective, and check the corresponding information flow inside the transformer under COT. So it goes in this way. So let's say initially the transformer is given some prompt, some input tokens, which is indicated by those green vectors. So then with the green vectors as the input, the transformer can, do SEL, it can output, some vectors, the orange vectors. But those orange vectors are not the final prediction. there are just some intermediate results. And then the transformer can, extract some information from those intermediate results and append such information to the input. So now you can see the input now contains the original input, which are the green vectors, together with some information from the intermediate output. And then with the augmented input, the transformer can perform another forward pass and get some results, which could be also intermediate results, and then appended to the input again, and repeat this process. So after a few COT steps, it can hopefully get a better reasoning results and then output the final prediction. So that's how a COT works in a nutshell. And then what we are trying to do is we are trying to use the COT, the chain of thoughts technique, to extract some useful information from the unlabeled data through some iterative process. And then with the the results coming out of the COT process, hopefully we're able to have a better performance for the final prediction. Okay, so to enable the COT process, we first start with the embedding because this need to be designed carefully in order to make sure we're going to have the information we're looking for. So we first encode the prompt into a input embedding matrix H in this way. So this matrix H contains 3 blocks. The first block is so-called labeled example block. So here it contains all the xi, yi pairs up to xn, yn. And then the next block contains the unlabeled example. So we have all the xn plus 1 up to xn plus m. So this is the second block. And then the last block is so-called reasoning block. So we use this block to store some useful information, as I'm going to elaborate shortly. Okay, so now this is the basic structure of the input embedding. And we know that, okay, for the first 2 blocks, actually, we have, embed a vector pi here. So this, for each example here, we have a pi. So this pi stores the corresponding classification probability vector for the corresponding sample. So in other words, this is a vector indicating with which probability the corresponding sample is in the class 1, class 2, and so on and so forth. Okay. So and then okay, in the last reasoning block, we also have a vector denoted by Q here. So there are C columns here, each column here corresponding to one cluster. So basically, this Q vector contains the transformer's estimate for the corresponding cluster mean. So for Q1, it contains the estimate for the class mean of the first class and so on. So in total, we'll have those blocks, concatenated together as the initial input to the transformer. Okay, so now because of the COT prompting, so we're going to append some intermediate results of the from the output of the transformer to the input. So here we use TF to denote a transformer, and we use theta to indicate the parameter of that transformer. So then for a given input, which is denoted by h hat t minus 1 here. So this basically shows as the input sequence at the tth COT step. So with this given input to the transformer, then we denote the corresponding output as TF theta of this h hat of super t minus 1 here. So this is going to be the corresponding output of the transformer. So the output transformer, has the same number of columns as the input. So we're going to simply take out the last C columns of it. So the last C columns, remember, contains, the reasoning block. So we basically take the reasoning block of the output matrix out, and then we're going to append that reasoning block into the, into the input matrix. So now after T steps, then you can see that this is how the input matrix H hat super T is going to look like. So it contains the original labeled and unlabeled data, the original reasoning block, as well as those intermediate reasoning blocks that are extracted from the output of the transformer. And then for each reasoning block here, what really matters is the Q matrix. So here in this Q matrix, it stores the current, the estimate about the mean centers at step T. So if from step T, you basically have an estimate mu1, mu2, and so on and so forth for all the class centers. So now, this is how the input of the transformer is going to evolve during this COT process. So if we repeat this for capital T iterations, then we're going to read out the final estimation of the mean centers of the class centers from the final reasoning block. And then with the, mean the class centers determined, we can then label each unlabeled data based on the maximum likelihood estimation. So this is, reduced to minimum distance type of classification because of the uniform assumption. So this is the, how this, process goes under the COT prompting. And we actually showed that there exists a 4-layer transformer such that its output sequence at the T+1 COT step is can be expressed in this form. So this is, so you can see the red term here, the term in red, basically is the initial estimate about the class centers based on the label data, because for all the label data, we know, which class one sample belongs to, so we can, based on all the samples within the same cluster, to calculate its center. So this is basically what we can have, initially based on the label data, and then after that, the transformer actually iteratively refines its estimate about the class centers, as in the blue term here. So in this blue term, we have PIJ, which is the estimated class membership for sample J. So as I mentioned previously, so this is embedded in the H matrix, and it tells us how likely this sample J falls in class I. So this, basically is an estimation about the distribution or probability for the class membership. And then with this estimated class membership for each of those unlabeled samples, we can refine the mean estimate, the center estimates mu I according to this blue formula here. So this is what the this transformer can perform during this SAL process. So essentially, this 4-layer architecture is designed to mirror an expectation maximization iteration for a Gaussian mixture model. It seems complicated because it has 4 layers, but actually each layer, has a particular role here. So for the 4th layer, which is the last layer, it basically contains the initial, calculates the initial estimates about the class centers as indicated by the blue, by the red expression here. So as I said, it's based on labeled samples only, and it remains inactive after first COT step. So this is like an initialization. And then with the initialization, the first layer will utilize, the estimation to compute the estimated class membership, PIJ, for each unlabeled data points. So this is so-called as expectation step, and this is what the first layer is trying to do. And then the second and the third layers basically performs the maximization step. So they're trying to obtain maximum likelihood class mean estimates, mu I, through gradient descent. So essentially, they are performing one step of gradient descent based on the class membership inferred from the first layer, and also the estimates, the current estimates about the the class centers. So when those four layers of transformer layers assemble together, we can essentially mimic the iterative EM process, so that after a few steps, a few iterations, we can have a refined estimate about the mean or the center of the classes, so that the geometric structure about the input data can be leveraged for more accurate classification. Okay, so that's the expressiveness of of the transformer. We also theoretically characterize the label prediction error bound. So we consider the so-called excess risk. So here we consider R star as the prediction error, and the Bayesian optimal classifiers with known class mean vectors. So this is the best we could hope for, essentially with the known class mean vectors or class center vectors. And this P indicates the corresponding classification error with fixed centers. And then we show that, compared with the best Bayesian classifier, our ICL approach, basically the discrepancy or performance degradation or the excess risk is upper bounded by this big O term. So in this, in this bound, so basically this excess risk scales in the order of 1 over square root of capital N times polynomial of m. So n is the number of labeled samples, and the polynomial m, m is the unlabeled samples. So this is shows basically how this excess risk is going to decay as our n and m increase. So if we compare with the excess risk for any classifier trained on labeled data only, so existing results show that this excess risk actually has a lower bound, which is omega of 1 over square root of n. So which means for the worst case scenario, the best case, the best classifier can, even the best classifier will have error scales in this order 1 over square root of n. So you basically cannot beat this scaling 1 over square root of n. But our results shows that the corresponding excess risk can actually be improved with a factor of 1 over polynomial of m. So this additional factor 1 over polynomial of 1 over square root of polynomial of m indicates that by leveraging the unlabeled samples during ICL, we can actually strictly improve the corresponding performance. So this is, our theory indicating the benefit of utilizing the unlabeled data in the prompt. So with this existence results, one natural question is, so how can we explicitly obtain such a transformer through training? Because our previous results indicates that we can have such a transformer that essentially mimics the EM process. But how could we train a transformer starting from scratch to make sure that it indeed can perform such a EM iterations during this COT prompting? So that requires us to do some training. And in order to make sure that the trained transformer can have the desired, behavior, such as mimicking, the trajectory of iterative updating, we adopt teacher forcing training procedure. So the idea is, so we're going to we are going to have a reference algorithm indicated by this ref here. So we're going to use this reference algorithm to generate some trajectories that contains the iterative updating of the class means or class centers during this EM process. So now we have if we apply this algorithm for on top of this given input, we will have a sequence of mean estimates for T steps. So we denote this as F reference of D here, which contains, basically, the trajectories of all the mean estimates, and, indicating how they evolve during this process. So now with this reference trajectories, so we're going to construct a reference embedding sequence. The embedding sequence has a very similar structure as we had during the inference stage. So we're still going to have those blocks. And then the difference is right now the reference block contains the output of the reference algorithm. So all the the reasoning blocks contain the corresponding mu estimates from the reference algorithm. And then, so essentially this will become the input of the transformer. And then with the input to the transformer, we get the corresponding output. So we extract the output, which, corresponding to the updated mu estimate. So we want to make sure that this updated mu estimate under this transformer forward path is going to stay close to what is obtained under the reference algorithm. So intuitively, by enforcing the output of the transformer stays close to the output of the reference algorithm, we would hope that the transformer is going to behave similar to an EM style iterative algorithm. And then we, with this loss function defined in this way, which is, basically aggregated error over all the classes and all the COT steps. So we can perform gradient descent, based on the samples, and then we can analyze the corresponding training convergence on the population loss defined as the expectation of the empirical version. So we characterize the training convergence of such a teacher forcing based training procedure. So we know that, for those 4-layer transformer, although it has 4 layers, but 3 of them, the last 3 layers are actually data independent, which means, we don't have to train their parameters. We can explicitly specify those parameters because they have nothing to do with the data. And then the first layer is data dependent, which means, the parameters of the first layer should be learned. So then we, do some initialization, random initialization, and then we do gradient descent on the corresponding empirical loss function. And then we see that we can explicitly show that the tunable parameters of the first attention layer, which is denoted by W here. So this W will essentially converge to the data dependent precision matrix sigma inverse here. So sigma, remember, this is actually the noise of the noise covariance matrix of the data. So which of course is data dependent. So it has to be learned. And then this results shows that WK will converge to this quantity at this rate. So this is the linear rate, which indicates that this is a very fast convergence. and actually this sigma inverse is the desired parameter for the attention layer in the originally constructed 4-layer transformer. So this results indicates that, okay, if we don't know the data distribution, if we start from scratch by doing gradient descent type of training using the teacher forcing technique, we can ensure that, you know, the desired transformer parameters will emerge out of the training. So those are some simulation results. We consider a simple case where we have 3 clusters, and we have, you know, for each prompt, we have n labeled examples, and we consider in total 5 COT steps. And then we vary the number of unlabeled examples. So when M is 1, it basically is the standard ICL. And when M is 10 or 20, that means, you know, we have more unlabeled examples in the prompt. As we can see from this figure, for class mean estimation, the error actually, you know, decrease as M increase after, you know, a sufficient large number of iterations. So which indicates that, you know, as predicted by our theory, indeed, the ICL performance is going to improve as M increase. And similarly for the label prediction accuracy, again, you know, it improves as M increase as well. So those are the theoretical parts, which validating the positive impact of including those unlabeled examples for augmented ICL. So next, I'm going to show how this idea can be actually adopted for a practical application, which is the wireless symbol detection here. So let's consider a standard wireless communication systems where we have input ST. So that's the input is basically, you know, signals randomly drawn from a constellation. So for example, if we consider QPSK or 16QAM, so the input signal ST is 1 out of those 4 or 16 symbols. And then it passes through the channel, you know, which is characterized by this channel matrix HT. And of course, it will, you know, be corrupted by some random Gaussian noise as well. And then essentially, eventually the receiver is going to receive RT. Okay, so this is a quite standard, you know, communication channel. And then we consider a block fading model. So block fading means that so the over an interval of some time slots, the corresponding channel matrix stay the same. So essentially, so this HT is going to be equal to some fixed H matrix during a so-called block or frame. So and then within each block or within each frame, the corresponding you know time slots will be divided into 2 parts. So one part is going to be used to send the pilot signals. So for pilot signals, essentially, you know, it's fixed, and both the transmitter and receiver knows the symbol, the transmitted signal. And then follow the pilot symbols. There's going to be another you know block sending the so-called payload symbols. So each frame, you know, basically contains such a, you know, such a structure. So pilot symbols followed by some payload symbols. So of course the payload symbols are information bearing. So the receiver doesn't know the, you know, the transmitted symbol, and it has to infer the transmitted symbol based on the received signal. So here we assume there are n pilot symbols and m payload symbols in each frame. And then we can see that this demodulation task or symbol detection task is actually, you know, can be naturally formulated as an ICL problem. So here in this formulation, the transmitted data symbols are, you know, the desired labels because, you know, they're from a discrete constellation and they are, you know, they are information bearing. And then all those received observations, R1 up to RB, they're basically, observations or features. So for all those pilot symbols, the receiver knows both the transmitted symbol and the received symbol. So those are, labeled examples. And then, so then essentially, we can formulate it as an ICL task where the prompt is defined in this way. So it contains all the labeled symbols for the pilot symbols and all those payload unlabeled symbols. Okay, this is a typo here. So anyways, so now you can see it matches with the augmented ICL formulation. And then, to decode those payload symbols is essentially to, predict the labels for all those payloads. So we, we can use the ICL, the augmented ICL idea to solve this problem. So we consider two variants of the augmented ICL formulation. So the first one is to apply augmented ICL at the frame level, which means that, we're going to allow bidirectional attention. So then each decoding, the decoding of each symbol, it can utilize all the received symbols within the same frame. So then mathematically, we define the training loss in this form. So we consider all those payload symbols. And then for each payload symbol, we're going to use a transformer to predict the corresponding transmitted symbol. And this transmitted symbol is going to be compared with, the training true transmitted symbol, because during training, we assume such information is available. So we use cross entropy to measure the prediction performance, and we sum over all the prediction over all the payload symbols. So now this becomes the loss function, and we can train a transformer based on this loss function. So once this transformer is, is trained, we can use this to perform simultaneous prediction for all payload symbols in the same data frame. So this is one variant. It's pretty much similar to what we discussed in the theoretical formulation. And we also consider another variant, which is augmented ICL with causal attention. So for causal attention, we mean that we only use the up-to-date received symbols to do the decoding. So we don't use some future symbols to do the decoding, even though they are, in the same data frame. So then the corresponding input to the transformer is a little bit different from the original one. So you can see that if we want to decode at the T's position, the T's payload symbol, then we only use all the received information up to this time T. So we ignore, all the remaining, symbols that you might receive in the future. So then we apply the cross entropy again based on the prediction and the ground truth label, and then we train a transformer. So essentially, if we do it in this way, then the transformer is going to predict the corresponding symbols, the payload symbols, in a sequential fashion. So this is similar or compatible with existing wireless receiver architecture. So, we show some experimental results here. So we consider two baselines. So one is so-called MMSE. So in this scheme, we basically use the pilot symbols to estimate the channel, and then use the estimated channel to do the symbol detection, which is the very traditional approach. We also have another approach called defined. So this defined is another ICL approach, which is, our original idea. So this approach uses the pilot symbols to decode the payload symbols sequentially, and then feed the decoded symbols to the transformer to predict the next symbol. So essentially, this is this is like, in some sense, use ICL to generate pseudo labels in some sense. So we can see that the defined algorithm, which is the blue curve, so it has a monotonic decreasing performance as the input symbol index increase. And this purple one, which is the augmented SAL, with causal attention also has a very similar behavior, but the corresponding error rate is actually lower than the defined baseline. And then this green straight line indicates the performance for MMSE based decoding. So it's you can see that the SEL based performance are better. And then there's also a red dotted line here. So this is the performance for the augmented SL approach with full attention. So this is, we use full attention to decode all the symbols simultaneously within the same frame. So you can see that, obviously augmented SL with full attention is the best. Which is natural because it utilizes all the information contained in the same frame. But for the other SL approaches, their performance actually improves as the symbol index improves. So this is because as more and more symbols are received and utilized, you can have better or more accurate estimation of the current symbol. So similar behavior is observed in this figure as well. So in summary, so today I talk about augmented SAL from both theoretical and the application perspectives. So we show that some provable performance improvement can be obtained using COT prompting for augmented SAL. And we also show that this idea can be adopted for wireless symbol detection with performance improvement compared with traditional MMSE-based approach. So this talk is based on some of our recent results. So one is published at this year's NeurIPS, and the other one is currently under submission. So with that, I think I can conclude my talk here, and I'm happy to take any questions you may have.
Yeah, thanks a lot, Jane. That's very wonderful. So we do have a few questions here.
Sure.
Maybe we can actually unmute Sam and
Yes.
Shauna, both of my colleagues here. So Jay, if you can help with that.
Yes,
So
I can.
Shauna, you have a question. Maybe would you be able to speak? I think the question is there any requirement on the number of classes and data distribution from each class? Does the dataset include labeled data from each class?
Yeah, so
mhm.
okay, so I think for the theory, so first of all, the theoretical part, right? So I mean, I don't think there exist any requirements for the number of clusters or number of classes. But we do have some requirements on the N and M here. So so yeah, I didn't I didn't explicitly specify the corresponding requirements, but essentially we don't want this N and M to be too small. So you would like to have N and M to be sufficiently large. So there is a scaling for N and M. So I think the scaling may inherently relate to the number of clusters. So essentially, if the problem becomes more challenging, right? If C is large, the problem becomes more challenging, then you would expect that N and M can, the requirements could be larger, right?
I see.
Yeah.
So is there any like empirical, based on your experience so far, any empirical number about, let's say, if the number of classes, say, relatively speaking, to have good performance, what kind of an aim may look like? Oh,
So
so
yeah,
just
I think
okay.
so here I think this could be could give us a certain indication about the impact of class numbers, right? So this figure is 16 QAM, which means you have 16 clusters, right? And the other one is 64 QAM, so which means you have much larger number of clusters. But in order to, as we can see, so I think so here the lowest is like 0.008. This one is slightly higher, but you could also know that this SNR is also much higher than the previous one. So the first one is 30 dB, this one is 35. So essentially, if you have more clusters, then you would expect a higher probability of error.
Right.
Yeah.
But the number seems to be doesn't need to be very large actually, right? When the maximum here is 20, right? If I get that correctly.
Yeah, so 20 is the number of payload payload symbols. Yes.
Yeah. Okay,
So
good.
here, actually, I didn't mention this, but for both of those two figures, they're based on one pilot symbol. So you only have one pilot symbol, which is the minimum we could have. So with one pilot symbol, if you increase the the payload symbols, then you have better and better performance.
Right. Okay, great. Thanks, Jing. Okay, another question from Terry Guo. So the question is, what's the percentage of the pilot over payload?
Yeah, I think that was answered just now, right? So N is 1, but M, maximum M is 20. So here we have 20 payloads and 1 pilot.
Yeah. So I think we have Jonathan. The question is, probably the question is, we kind of use transformer for in-context learning. Maybe the question is, have you considered other machine learning models for the in-context learning, or is it large language model the only or best choice today? Any other models that could have similar capabilities?
For that, I think in-context learning, so this concept was brought up, I think, a couple of years ago, based on some observations from the GPT-3 or 2 models. So I think it emerges as a result of the large language models people are investigating recently. So I'm not sure whether similar behavior or capability exist for some other models. It might be, but I think nowadays people pretty much focus on the SL capability of transformer-based LLMs.
I see. Good. So actually for Sang, you wanna speak? You can unmute and speak actually. Also same for Terry.
All right.
I know you have several questions. Maybe that's easier.
All right. Thank you. I was wondering for the MMSE detection, did you assume the channel matrix H is known for detection?
We again use the pilot symbols to first estimate the channel. So MMSE is for channel estimation. So you can, based on the closed form expression, we can derive some closed form estimators, right, for the channel.
So
the MMSE estimator for the channel.
So you assume that is perfect?
There could be noise, right? So it's a noisy channel.
No, estimation of H. I mean, estimation of H is perfect.
It's MMSE. So it's not perfect. It's the best we can estimate.
No, there are two estimation. One is a channel estimation. The other is a data estimation, right? So for MMSE, this is for data.
This is for channel. We first estimate the channel. Yes.
So this symbol error rate is for pilot symbols or data symbols?
It's for data symbols.
I see. And for channel estimation, you use MMSE channel estimation, which may be incorrect, may not be perfect.
Yes, exactly.
And then based on that channel estimation, you made a data detection using your algorithm, right?
Use so based on the estimated channel, we can we can inversely estimate the transmitted symbol, right?
So that's a classical communication method.
Yeah, it's
essentially.
a classical communication approach. So this approach does not involve
As a
any
reference.
transformers. Yeah.
Mhm.
And then you also have another question, Sam. I guess the question was the intuition of how increasing M improve accuracy. Is that right, Sam?
Yeah. Is any intuition behind that?
You mean in this curve, we have both of those two curves decrease? Is that what you're referring to?
No. So if you have more
You mean
M,
okay?
increasing M can help.
You mean like
Yeah,
here we
yeah.
have okay. So intuitively, so this is what I could explain. So imagine, all those dots are, the unlabeled samples, right? So if you have more dots here, so then your class mean estimation would be more accurate, right? So because the clustering is based on, the unlabeled samples. So if you have more samples, although they are unlabeled, but they can exhibit a more obvious class structure. And with the clustering structure, we can have a better or more accurate estimation about the mean.
Got you. Thank you.
Sure.
Thanks, Sam. Terry,
Hi,
you can unmute and
a
speak.
very interesting presentation. Actually, I met you young in the ISIT. Probably don't remember me, but it doesn't matter.
Yeah, so if you can turn on your camera, or if
Really?
that's feasible,
Okay.
then
That's
you will see.
okay.
Yeah, go ahead. Sorry. Yeah.
Oh, okay. Here.
Yeah.
Yeah. So I've seen your use like over.
Oh yeah, okay. Yeah, I remember. Definitely, I remember. It's just in the summer, right? A few months back.
Yeah. It's very hot. 30 dB SNR is very high. So is that
It
any
is.
reason, and how do you justify that?
We do have some results at lower SNRs, but probably they're not as good as what I showed here. So I basically cherry picked some applause here. Yeah. So currently, I mean, because our simulation are based on, I think, not very large, pilot. So we only have one pilot symbol. So that's, intuitively, why here we boost the SNR in order to have a good performance. So if we increase the pilot symbols, which, are the labeled samples, then the corresponding requirement for the SNR can be reduced a little bit. So, we don't have to use a very high SNR.
Okay. All right. I think that is the trivial thing. Maybe in the future this can be improved. But anyway, this is
definitely.
It's a totally different direction of, based on from my point of view. I'm a physical guy. I do demodulation. So now you guys totally take a job from us. So
well, no, I'm a communication person.
You get a
I'm from
new
the
job.
same community. I'm from the same community. It's not like I'm taking anything away from this community. We're trying to introduce some new ideas from other
this is very,
communities
very
to our
interesting.
domain.
I think that's a very good direction to look at. Thank you so much.
Thank you.
Hey, Jane, I have a simple question. Thanks, Terry. Good to see you here. So I think I forget the slide number, but when at the earlier part you mentioned this embedding mechanism there. I think so. For the unlabeled data, there's the classification probability vector, right? So that vector is that coming from the training, or where would that come from?
Yeah. You mean this part?
Yeah, go one,
this
one more.
part.
Yeah. The
this part, right?
Pn+1 and Pn+m. Is that coming from the training stage itself? Or
Yeah,
this?
that's a very good question.
Yeah.
So first I would like to, I didn't elaborate this, but what I want to point out is, so here for the theory part, right? So because we need to show those bounds and convergence rates, so we could not have very, complicated architecture or, very complicated, data structure. So that's why everything is actually simplified. So we have, we have the particularly designed embedding architecture here, and then a particularly designed transformer architecture, so that we make sure after we pass such an input to the transformer, we get exactly what we are looking for, right? The updated mean estimates, essentially. So we iteratively update our mean estimates and then improve the final prediction. But in the application side, we actually relax all those assumptions. So we didn't do any particular, embedding or particular chain of thought based prompting or, teacher force and training. So you can see that our loss function is defined as, very simple. It's just the cross entropy loss, right? So in other words, we let the model to do the job itself. So we do not explicitly, ask it to perform exact the EM algorithm we're trying to, trying to perform. So in other words, we don't know exactly what transformer is actually doing if we set our loss function to be in this way. So our theory is just, provides a more principled, perspective to explain, to argue why, by including those unlabeled samples can help. But in practice, if you really want to use this idea, we don't have to, follow exactly the same architecture of the transformers or the architecture of the embedding in order to show the, benefits of this approach.
Okay, I see. I guess another question, yeah, I guess you used the classification problem as both intuition, right, which is very, very helpful, and also for the empirical result here. So I guess I'm curious in general, like for in-context learning, right? Besides classification problem, what are the other types of problems that can be very, very effective? Maybe could even be used in, I'm thinking some of the resource management settings, like in the network setting. Has there been any trials along that direction already?
So I so that's a very good point. So I think that's a very important direction regarding how large language model can be utilized in the domain of networking in general, right? So my understanding, so for those problems so far we consider those are relatively simple, right? Because symbol detection, it's a simple classification problem. We can probably extend it to regression problems like linear regression, right? Which also is quite straightforward. So we would expect that, some sort of performance guarantee can be obtained for those simple tasks. But for resource allocation, I gave this a little bit of thought, during the summer. So my understanding is resource allocation is in general much more challenging, right? Because it's not a simple classification problem. It's actually decision making, right? It involves, essentially some sequential decision making process there. So then I gave this a little bit of thought, and then eventually I think my thought is, okay, maybe reinforcement learning is a better approach for problems like
In that
that,
context,
because of all the decisions and the interactions between your decision, the environment, and the performance. So usually it's a more it's not like a simple one-shot optimization problem, in my opinion. So and then to handle the sequential decision making, there are existing works showing that in-context learning can actually do that. So people have done some theoretical studies showing, okay, if you train a transformer or large language model properly, then it can still, you know, mimic certain reinforcement learning algorithms. So essentially, it's still hopeful that, you know, ICL can be applied to solve similar problems. So I actually asked some of my students to study the so-called decision transformer, right? Decision transformer, you can say that it's trained to make decisions.
Yeah.
So we did some investigation, and there are some literatures outside, you know, studying decision transformers as well. My current feeling is it's a promising direction, but it's still, I think it's much more challenging for sure. So we have to maybe you know, think of some new elements, you know, so that it can help improve the performance of decision transformer. Because the training of decision transformer is a little bit different from reinforcement learning. You know, for reinforcement learning, we have dedicated, like, you know, policy network critic, you know, so you have a way to tell you how good your policy is, right? And based on that, you can adjust your policy. But for decision transformer, currently doesn't have an explicit mechanism to tell you how good your action is, you know, based on my understanding. So I think, you know, some innovation is desired, you know, for such, you know, scenarios. Yeah.
Let's see if we actually you will solve those hard problems pretty soon. Could that methodology be something we can potentially use to? I guess I'm thinking about the scenarios where, you know, kind of this sequential decision problem where the whole environment changes potentially, even potentially at a fast time scale, right? Could that be something that can potentially to help with the convergence and those? Like when it changes, RL sometimes takes too long, right? So that it cannot potentially be useful in those fast varying settings. Could this be like, if this decision, what you call the decision transformer would work, could that be one way of addressing those highly varying environment?
So decision transformer, currently people have, I think in some sense, decision transformer is like a multitask decision maker. So it's more robust based on my own observations as well. So my student did some training of the decision transformer and the testing. So what she observes is, so if during the training the transformer is exposed with many different environments, right? So it's like a multitask training. So you have data collected from different environments, and then we threw all those data, you know, into the transformer and let it train. And then turns out transformer is more robust. So then, you know, if it encounters some new environment, then it usually can perform better than you know, a standard RL or a standard like a transformer which is trained based on a single environment.
Right.
Yeah. So I think there are. Yeah, there are capabilities that can be leveraged or explored of the transformers. Yeah.
Great. Yeah. I'll try to catch you on with some pointers maybe later. Any other questions, folks? I know we run a little bit over over time. Any other questions, folks?
Quick question.
Yeah.
So the symbol error rate with MMSE, that was around 0.16, on the order of 10 to minus 2, right? Is it? I'm wondering. We know the symbol error rate for 16 QAM in fading channel with optimum detection. How far is your curve compared to that optimal detection symbol error rate?
So what do you mean by optimal?
So maximum likelihood detection. So we know that is optimum decision rule.
So I think that's pretty much what the classical approach does, right? Classical MMSE based approach does.
Yeah, nothing can beat that optimum detection. That is the absolute minimum error rates.
I think that is what you would do if you utilize the pilot, right? If you use the pilot,
Yeah,
use
we
the
do.
pilot.
Right. So we have some mechanism to estimate the channel, and then based on that channel information, we make a optimum decision, which is a maximum likelihood decision. So we know what the similar rate with that optimum decision rule for given channel gain H. So I was wondering, you have a nice curve approaching to some 0.08, a 0.0 on the order of 10 to minus 3. So I'm wondering if how that low limit in your curve compared to the SCR with the optimum detection rule, which we already know that similar rate.
I think what you described, like, you first estimate the channel, optimally, which is essentially MMSE, and based on that channel estimation to do the decoding, that would give you this green line, right? So that is what we would have, if we don't utilize all those payload symbols. And then the bottom line is what we would have if we utilize all the received payload symbols to do the joint detection, essentially. So that's what we achieve using this augmented ICL idea. So I think that roughly tells us, how far or how much improvement we could have by using ICL compared with the classical MMSE based approach. Whether, there are better classical ways to utilize the payload symbols to improve the, decoding performance. I'm not sure. I'm not sure what are the, classical approaches to do that. So my understanding is usually you do it in a two-stage process, right? You first estimate the channel, and then based on the channel, you do symbol detection.
Right. Yeah, that's the current stance. But the gain you provided from going down to audio of 10 to minus 3 is by utilizing additional data, which is unlabeled data.
Yes.
So the difference between the green and the red curve, red lines are using unlabeled data. Is that right?
Yeah. Yes. That's
Okay.
essentially the benefit of utilizing unlabeled
Okay.
data.
Yeah. So without having additional unlabeled data, we do know the symbol array. That is what you're saying is the green line. I see. Okay. All right. Thank you.
Thanks.
Right. Thanks, for staying with us for this extra time. Jing, I know we are already over time for the both. Do you still have a few minutes, or you
Yeah,
have other
sure.
commitment?
I'm okay.
Maybe we can join the other meeting room. That's
Okay.
just the internal folks small
Okay,
group.
sure.
We can do. Yeah, we'll see you there in 30 seconds.
Okay, sure.
All right. Thanks, everyone.
Thank you. Bye.